For problem number 12, we've got a battery with a voltage of 18 volts. Resistor is 1.2 times 10 to the fifth. Capacitor is 9 times 10 to the negative 6. And we want to find the energy stored in the capacitor, which, because I have capacitance, and it says after a very long time, I know that the voltage through the capacitor is also going to be 18 volts because it's going to be a roadblock, and this is not going to have any voltage drop because the current is 0. So in this case, Q is equal to CV. Oh no, I am trying to solve for the energy. So U is equal to 1/2 CV squared, which is equal to 9 times 10 to the negative 6, divided by 2, and then my voltage is 18 squared. So I get 0.00146 joules. Next, we've got the spacing between the plates increases by 3, and it says the change took negligible time compared to the time constant. So this statement lets us know that Q is constant. It has not yet changed. And so when we talk about the spacing, we know that for this scenario, we are going to analyze this capacitor equation. So kappa epsilon naught A over D, which lets us know that kappa is inversely proportional to D. So if D increases by 3, capacitance decreases by 3. So C nu is equal to C over 3. Now, the next thing we need to analyze, because if we're asked to figure out the work is equal to change in energy. I already calculated the original energy, so I need to find the final energy. So I can use the same equation, but I do need to figure out what is changing. So I said the charge stays the same, and so I'm going to analyze C equals Q over V. If the charge stays the same and the capacitance decreases, then that means the voltage needs to increase. So the new voltage is 3 times V. So that's what I'm going to plug into my expression. I am going to plug in my appropriate values, which are 1/2, and this is U final. So U finals with the new capacitance. C over 3 times 3V squared minus the original, which is 1/2 CV squared. And I can simplify this down as 3/2 CV squared minus 1/2 CV squared. And in the end, I get just CV squared. So I take 9 times 10 to the negative 6, multiply that by 18 squared, and I get 0.00291, or 292 is what it rounds up to. Okay, so that is how much work is done. Now we need to determine the current in the resistor immediately after the spacing is increased. So I'm going to go up here and I'm going to change these values. The capacitor is decreased by 3, so that means this is 3 times 10 to the negative 6. The voltage has increased by 3, so that makes this 54 volts on this capacitor. And in order to find the current, I can erase the fact that the resistance is not going to dissipate any voltage there. I can actually use the loop rule for this one. So what I'm going to note is that a capacitor is like a battery. If the battery is charging up the capacitor, if the battery is charging up the capacitor, this is 18, from this side, that means it's going to charge up all the positive charges on the top of the capacitor here. I know that this has 54 volts pushing upward, and this has 18 volts pushing upward. I always follow the voltage that's stronger because I know that's going to overpower the battery. So in this scenario, I'm going to create a current going up to the left and down, and then it's going to go to the right and then up. And it doesn't matter what direction your loop is. I always like to make the loop in the direction of current to make my life easier. And then we just do the loop rule for part C. So I start at the capacitor. That gives me 54 volts out of the negative into the positive. I'm going to go through the resistor, which is my loop is going in the same direction as current. So it's negative 1.2 times 10 to the fifth times I, which is what we're solving for. And then I'm going to go into the positive side of the battery out of the negative, so that's minus 18 equals 0. When I do that loop rule, I end up with a current that is equal to 36 divided by 1.2 times 10 to the fifth, and that gives me 3 times 10 to the negative 4 amps. All right, now it says after a long time, the circuit reaches a new static equilibrium. Okay, so I'm going to go in here and change some of these because after a long period of time, the battery, which is providing the voltage constantly, is going to eventually counteract the capacitor because the capacitor's energy only lasts for a short period of time. And once it is fully dissipated through the resistor, then it's just the battery providing the voltage. So again, the capacitor is going to be charged up by the battery at 18 volts, and that would be equilibrium after a long period of time. Because again, that extra charge on the capacitor has dissipated through the resistor. So in this scenario, we're trying to find the total charge passed through the battery. We went from 54 volts down to 18 volts. And so that change is going to represent our charge. So I'm still going to use the capacitor equation. C equals Q over V, or Q is equal to CV. My new capacitance value is 3 times 10 to the negative 6, and my voltage, which is the voltage that has been dissipated when it went from 54 to 18, is going to be 36. So when I calculate this, I get a charge of 1.08 times 10 to the negative 4 coulombs. All right, part E is trying to find the energy added to the battery. So when we're talking about energy added to the battery, we can use the energy equation Q delta V. The battery has a change in potential through its positive and negative terminals, and we already know what charge is going into the battery. So we can just take the 1.08 times 10 to the negative 4 and the change in potential across the battery, multiply those two together, and you get 0.00194 joules. And that's it.